Okay, let me start with first thanking the organizers for inviting me. I'm particularly happy to be here simply because I had some minor visa problems, because I look like a serious terrorist, of course. But nevertheless, I made it, and I'm looking forward to hopefully having some discussion afterwards. And I'm going to talk about flying colloidal carpets. Now, let me just point out that most of the work had been done by Nienke Geerts, who is now in Yale doing a postdoc work. And recently I had a very nice new PhD student, Sabrina Jan, who is has a background in biotechnology. And she is very good with handling the biological or DNA samples we work with. The work has been started back in Amsterdam a few years ago, but much of it is now carried on in Cambridge, where I'm located at the physics department. Okay, now my introduction will be a bit long, and I will also add a few new things there in my introduction, just to introduce to you the topic of DNA-coated colloids. And one important thing is what we would like to use is DNA as a smart glue to drive colloidal aggregation. Now, why DNA? And people have worked with polymers and DNA, polymers and colloids, but DNA gives a bigger option as a specific glue, because it has this double-stranded structure here. You have two separate backbones, and they have these bases. And what is important is that they are running counter-parallel. So the phosphate group is on one side, whereas the other side is called 5' end, the other 3' end. And what you also have is that these bases, you have only 4 bases in DNA, G, C, A, and T, and only G can bind to C or A to T. And that gives the DNA a real specific structure. That means it's like a barcode. If you take one side, only a complementary part to that will bind appropriately to that. So double-stranded DNA is highly specific. What is also important is that these bonds in between are only hydrogen bonds. So that means they are thermally reversible. You can break them apart when you heat the whole system up, and you fuse them back when you cool it down. Now that was first used actually by Ned Seaman in the early 1990s, where he started to use DNA, short strands of DNA, single strands. And for instance, here you have 4 different strands that are complementary to each other, only in a few bits, such that you can make a tile, a 4-way junction, which is also called the Holiday junction, that then binds to form larger structures. Recently, people have also made these nice cages that can be perhaps used to encapsulate molecules inside. But people have come up with all sorts of beautiful structures in the past, 10 years, say, based on these DNA, short-strand DNA tiles, to build mostly 2D structures, even smileys. Here the map of the United States and North America and South America. Here I should be more careful with my wording. And only recently people started also making 3-dimensional scaffolds, pure DNA scaffolds. But so why do we want to not use these type of structures, but DNA with colloids together? And there I continue with my little introduction here. pointing out that actually the first people who have worked with this were the group of Merkin and the group of Alivisatos, who had back-to-back publications in the same, I think, Nature issue in 1996, and they were the first to code short bits of single-stranded DNA to roughly 10 to 50 nanometer gold colloids, and they had a second population with non-complementary single-stranded DNA attached to it, and in solution, in the absence of any complementary binding agent, they wouldn't aggregate. Only when you add then these complementary part that holds both complementary parts to this single strand and to this single strand, you start to form aggregating clusters or aggregating colloids into clusters, and they are nicely thermoreversible. Now, I come in a sec to the reason why people try to use colloids, because in principle you could do that also by taking the single strand and attach a single fluorophore to the end, and then have another patch of DNA on, say, a chip on a surface, and you have the complementary parts here in the solution, the target linkers. When you cool it, these will bind only in the region where it is complementary, but not in the other regions. And when you heat it off, it falls off. So the fluorescence, sure enough, you can detect easily. But what if you want to detect now not just this binding and unbinding event, but you search directly for single base pair mismatches, so some faulty DNA in your system that you want to screen. Now, when you have this system, what you can do is you look, for instance, at the hybridization strength, the number of hybridized bonds formed by, for instance, looking at the adsorption of double-stranded DNA with 260 nanometers. And what you get is something like a hybridization curve or melt curve. This is the percentage of hybridized DNA, so a number of double-stranded DNA formed. If it's here, then it's in the single-stranded form, and this is simply the temperature. So what happens is the black curve, what you see is when we have a perfect matching target linker to our fluorophore labeled single strands, and you obtain this melt curve here. But if you introduce a single mismatch in the system, the whole curve shifts to slightly lower temperatures. Now, the difference between these two curves is fairly small to detect. And so although there is a difference, it's still not good enough for detection. Now, when you do the same, but now you have the same single-stranded DNA attached to these nanoparticles here, what happens is, for the same concentrations and the same sequence, you get a much sharper transition. And when you introduce now on will a single mismatch, you see that any shift to lower temperatures will give a significant difference between the correct and the mismatch, the one containing the mismatch. So by introducing this colloids, there is something happening to the sharpness of these melt curves. Now, I'm personally not working with this system, but we did struggle with the sharpness, with the steepness of this curve, and I just try to give you a small reasoning for why this is happening. Now, again, Merkin showed that if you take this gold nanocolloids and you coat it only with 30%, roughly 30% of single strands, your melt curve is given by this one. It's still not that sharp, but as you increase the number of strands on that curve, it gets sharper and sharper. Now, this is very interesting. So you have here a sharper dissolution profile and a higher dissolution. Also, what happens is it's not only getting sharper, but the inflection point here is moving to higher temperatures. Although you keep the same bonding, hybridization bonding strength between the individual single strands. So what's happening? Now, when you want to try to understand it, and there are loads of explanations in the literature making the salt or the counterion distribution in the system responsible, I think we can just simply look at it from a statistical point of view. If you take two colloids and now look only, for instance, at one holding one single strand and the other another single strand, and we have this equilibrium for different temperatures. High temperatures, it's falling apart. Low temperature, it's bonded. Now, if n is the maximum number of hydrogen bond pairs in the system, and delta little f here is the free energy difference between the bound and unbound single DNA pair, then the probability that you would that a single DNA pair is unbound is simply given by Pu1 is 1 over this 1 plus the Boltzmann factor here containing this free energy difference. What that means is that when we are at the transition temperature, what we call the melt temperature, which we would say, okay, it's the inflection point in our melting curve, then delta F goes to 0 at this point, which means the probability that a single pair is unbound is simply 1/2. That means only 50% of the pairs are bound at the melt temperature. Now, this is not the point where the two colloids will unbind completely, because you have plenty of these bonds in the system. So for that to happen, all the DNA pairs have to be unbound in order to truly melt your system. Now, the probability that strands are unbound is simply Pu of n of all these present hydrogen bonds has to be the probability of a single one to be unbound to the power n, the number of base pairs in your system, in the bridge between your two colloids. Or, in other words, when you write it down, it's simply an exponential of minus n times another exponential. And you see immediately why this transition becomes so steep. So it's a pure entropically driven sharpening of that melting curve. Because as we increase the number of bonds in the system, in the gap between the two colloids, the transition or the probability goes to infinity. So you see very quickly then, for single-stranded pairs in solution, they just have a simple Langmuir type melting curve, whereas if you have plenty of them bound to the colloid, then your temperature not only the melt transition only sharpens up, but also it moves to higher and higher temperatures as you increase the number of bonds that can bind between the two colloids. So you have an increase you have a sharpening of your melt temperature, and moreover, your melt temperature, you can show easily, is increasing logarithmically with the number of bonds between them. Now, this is very interesting because that may be also one of the reasons why it was until now very hard to actually really drive crystallization due to these hybridization or directed bonds between colloids using short-stranded DNA. It was actually only two years ago that the group of Gang and also Merkin showed that they showed first crystals of nanocolloids. There is also some work on large colloids, on micron-sized colloids by Crocker, I think. But it remains difficult. Although we have this high specificity, if you have too many of these bonds, you get a very narrow area where you actually can play in order to form crystals. Because if they bind so strongly, if you cool it down by a degree below your melt temperature, it sticks where it sticks, and it cannot re-anneal because there are too many bonds in the system. So you have to be very careful. That's an important thing. But if you can control it in a very good way, then this is a perfect system where you can start to play with specific bonds where you say, okay, I want to have a colloid A that only binds to B, or a B only to C, but A not to C. You can start to design any, in principle, any interaction topology that you would like to have using just, and you can construct AND or OR switches with using these specific interactions. Okay. Now, of course, as I just mentioned, people would be very interested to build very complex structures with colloids to form, for instance, photonic crystals. But that remained with this, what I just told, a bit difficult. People now work for it for 10 or 15 years, and it's still not easy to make anything more complex than a BCC or FCC crystal in the system. But then we were motivated by a theoretical work by Alexei Tishenko, who said, now wait a minute, we have these colloids, but what we need to anneal the system are very long spacers, polymeric spacers, and short-ranged attractive interactions due to the DNA hybridization. And by plotting, he made a phase diagram where he plotted an effective interaction potential against the size ratio of these big colloids to the radius of gyration of your polymers, stabilizing polymers. He says there must be a region where you can find hexagonal structures, BCC, square lattices, but also diamond structures, for instance. So we thought, okay, we can easily do that. And in order to do the whole thing not with nanocolloids, because that's hard to analyze if any structure forms, we thought, okay, we want to study that the aggregation in time. We go to larger systems, and the long spacer we use is lambda phage DNA with 48,000 base pairs and a complete contour length of about 16 microns. The nice thing is lambda DNA comes in, this is a double, indicating a double-stranded closed phage, and when you heat it up, only in this specific space, the backbones are interrupted, no covalent bonds, and it always comes apart in the right space. So you linearize it, and you create a long polymeric spacer with complementary sticky overhangs of 12 bases. We did that, and what is very nice these days, you can just then go and buy the complementary part separately already with a biotin attached to it, and you attach it to one side, you make sure that you ligate this covalently in the backbone here, because you don't want that part to fall apart later on when you do heat cycles. And this biotin can then bind to, say, we use fluorescently labeled polystyrene colloids that are coated with neutroavidin, and biotin binds very strongly to neutroavidin. So you can just mix this with your colloids and you end up with DNA-coated colloids in the system. Now, incidentally, we use tris buffer at pH 8 for all our samples, and we use actually sucrose solution to density match, because the polystyrene is slightly more dense than water. So in order to avoid any sedimentation effects, we use sucrose in the system, and that's worked very well. And the ionic strength was roughly 50 millimolar sodium chloride. Okay, the sizes, the colloids are 1 micron in diameter. Again, the radius of gyration of lambda DNA in this system is about 800 nanometers. So it's roughly the same size as our colloids. And we do the same with a complementary part, where we modify the other end of the lambda DNA to green fluorescent colloids, such that we can, in the end, form separately these and this, and when we mix them, they can only bind, and we make sure that red, like this, red cannot bind to red colloids and green cannot bind to green colloids, only red to green. Now, because DNA was absorbed from low concentrations, dilute concentrations to the DNA, to the colloids, we only end up with roughly 10 arms per bead. Now, just very briefly, we computed some of the interactions that are involved in the system. Now, if you would take just the bare colloids together and look at the van der Waals interaction at 1 nanometer separation, you get a very strong attraction, of course, minus 300 kT. The Coulomb repulsion in the system was amounted at 1 nanometer separation was about 80 kT, whereas the DNA binding strength between the 12 base pairs is about minus 25 kT in our system. Now, the steric repulsion we don't know, and we haven't been able to measure that properly at the moment. The way we image the system is what Dave Waits explained this morning, simply confocal microscopy. Like this, we can then later on reconstruct our entire system, first taking the image layer by layer, and then reconstruct the 3D image later on. Okay, now the first experiments were actually rather disappointing. We mixed red and green, and what we got after even a few weeks is size-limited clusters. And it was nice. We asked Dan Frankel and his group to do some simulations to verify why we have size-limited clusters. But it became, and they also doing simulations where they simulated the DNA as soft sphere with a sticky short-range potential. They also see size-limited growth, and that's simply due to the fact that the DNA is so long that even if you hold two colloids, red and green, next to each other very close, in time all the bonds will saturate between them, and you can't grow any longer. But moreover, there is no symmetry or anything beautiful about these clusters. They are just random clusters. When we introduced then, when we shortened the DNA in order to get continuous growth and not just size-limited growth, this is a low-resolution large image of what we can observe. And these are also rather random 3D clusters. You only see a slice through it, but it grows in top and bottom as well. Okay, so we thought, well, Alexei Tashenko was perhaps not quite right, or we got the wrong interaction potential here. So let's try with something simpler, and we went to a 2D system where we said, okay, we prepare a surface where we attach one of the complementary parts to the lower surface. This is polylysin PEG, coated then, terminated with biotin. We adsorb strapped evident to it, and to that on top, the biotinylated single-stranded bases here. As a control, will show you first colloids with the complementary part, just to see that we really get a nice homogeneous coverage on the surface. And then I show you what happens when we introduce to exactly the same system, but our long spacers. Now, as we expected, and remember, it's not sedimentation, it's really only when it happens to come close and feel the hybridization potential, then they can bind, but otherwise they just float around because we have density matching in the system. At room temperature, after a while, we see a very nice coating of the surface. When we heat it up, well above the melt temperature of a single strand, that's necessary because we have many bonds here. You see it comes loose, and it's highly reproducible. So we have a good surface coverage with our complementary single strands down there. Okay, so what I will show you next, you have to look very carefully to see what we do. What I want to show you is some stack going as you go with the confocal from the bulk solution, and you approach the surface from above and go slowly down. And that's what you see. A very different picture. It was a bit fast, so I'll show you the picture once more. And to our great surprise, we see actually some very nice 2D crystals. Moreover, when we look at the radial distribution function, we do see a nice hexagonal structure of that crystal. Now, the reason why you see here a bit of dark and bright lights, this is these are a number of stacks together. So dark spots were colloids that were a bit lower and the brighter ones were a bit higher. Okay. Now, it is well known that when you have free polymer in dissolution with colloids at low concentrations of colloids, free polymers can induce depletion due to depletion interaction, crystallization of colloids on the surface. But then they are really stuck on the surface. But what we observe here is, in time, that our crystals here are not at all really stuck, but they can move. And so then we just looked at the overall height distribution of these different crystals. And what I show you here is this is a number of crystals we observe, and their corresponding height, cruising height actually, because what you notice is the preferred distance is 2.5 microns away from the surface. Now remember, the radius of gyration of lambda DNA is only 800 nanometers, so you would, if it would be just depletion, it would be perhaps somewhere down here, but it's actually far away from the surface. Well, far away is maybe exaggerated, but certainly 2-3 diameters, stretch diameters of the lambda DNA. So this is one of the rendered samples of such a crystal, and you see how flat it is here. And so they are really nice, loose, two-dimensional colloidal membranes, well ordered. And what is very fascinating is they are really very, very stable. You would expect any colloidal membrane to crumple and unfold on itself when you release it into bulk, but no. When you can introduce a high sugar concentration to change the buoyancy, and you can lift it with buoyancy up, and they stay very, very stable for a long time, completely flat. But they show beautiful undulations, as they should, depending on their size. What is interesting is, so I told you what happened is we anchor basically the colloids to the surface through hybridization. So then we thought, okay, that's what we would do initially. But then we said, okay, let's remove the hybridization part, the sticky overhangs on both, on the lambda DNA and on the surface. We only have our polylysin pack surface down here and this, and we still get crystals. So there's no effect, perhaps, on due to the single strand binding. And when we now, the reason I think why this is still happening is simply that you only need a weak anchoring energy in order to drive this crystallization, but the anchoring attraction here is coming from the polylysin, which is positively charged, and DNA is negatively charged. So this is enough to just weakly hold the colloids close to the surface. Another important thing that you have to realize is in solution, when I have just in bulk, they will not aggregate at all because I have a steric stabilization layer of negatively charged DNA all around the colloids. So why close to the surface do they come together to form that crystal? So that means they must be anchored somehow to that weakly absorbing surface, giving the colloids enough time to explore each other and perhaps to overcome that steric stabilization formed by the DNA, because the DNA stays attached. So just to make our point that you don't need necessarily a positively charged surface, we also use the same with a completely different surface coverage, and there we used biotin BSA. BSA is a protein that is on the whole negatively charged. This binds nicely to a surface. We add then a strapped avidin here in this layer, and we make two layers. And on the top layer, we add our biotinylated single-stranded DNA overhang. And also in this case, we get very nicely ordered crystalline structures. And we did that also with a positively charged polyelectrolyte. And again, we get these very beautiful crystals. Now, obviously, there must be also some cutoff below which of this polymeric length that will stop this crystallization. So we went to shorter lambda DNA where we had a radius of gyration of 200 nanometers. Again, the same what I showed you before in the 3D images. And we still get crystals, but they are significantly smaller. And as you remember, when we have no spacers, you don't get any crystals whatsoever. So that's quite interesting. And just to summarize this part, what we show is we have 2D crystallization, and that in plane of colloids, not due to the specific interactions of DNA, that we have hybridization due to a specific binding, but rather it depends on a very long polymeric spacer. Now, what is very interesting is DNA is a super long polymeric spacer. Moreover, this super long polymeric spacer is monodisperse. You can't make man-produced polymers of that large length monodisperse. So DNA is actually a very nice long polymeric spacer, which is in addition monodisperse. you will need a weak attraction, but it doesn't matter what it is, to the surface in order to drive this crystallization. And once formed, they are also very stable in the bulk. So you can lift them up easily, and they stay totally inert. Okay, so as a next step, we thought, okay, let's try and make mixed crystals, or 2D crystals on the surface, where we have red and green colloids in the system. Moreover, like in the beginning, I allow green to bind to red colloids. And I have just a polylysin pack layer in the presence. And this is, again, lambda DNA. Now, again, just to remind you, initially we got these finite size clusters here in bulk. But now, when we didn't have any attractive surface in the system, now in the presence of our weakly attractive surface, we get that. So why on earth are we not getting red and green mixed crystals? I mean, that's really odd, because I do allow specific binding between red and green, and it does work. We have shown that in bulk before, that this works, and we get there always clusters with half red and half green. So that's very odd. Why would they now, in the same solution next to each other, form red and green separate colloidal carpets? Now, we were a little puzzled and repeated that experiment several times to be really sure that this is what we observe, and that it was not just simply a fluke. And then we decided to actually look at the radial distribution function of these systems. And remember, we specifically ordered our colloids to be exactly 1 micron in size. So we asked the producer to give us the same colloids, just different fluorescent labeling. But what we observed is that actually the green colloids are just 10% smaller than the red ones. And that was sufficient to drive segregation. Although you have an attractive binding between red and green, it is the size difference that drives them apart. So you have size fractionated crystallization. So incidentally, there was already some time ago work by Barra and Hansen who showed actually that if you have polydispersity in a colloidal system that is larger than 6% in 3D, you will not get 3D crystallization. Polydispersity of your size polydispersity of colloids will destroy crystallization. Now, then some simulations later on showed that actually in 2D, this is broadening, and you can accommodate up to 10% polydispersity in the system, but not more. And we just by accident hit that transition, and we get red and green colloids, crystals. Now, okay, we thought, okay, let's see what happens now when we shorten again the polymeric spacer, and we go to 200 nanometers. That means also you have, in principle now, not just 10, but roughly 28 stickers per colloid. And here, what we observe is just the regular thing. What we observed before in bulk, we just get random clusters. Before they even have the time to come and explore the surface, they have formed already these clusters, random clusters in solution, in bulk. So actually, what I showed you before, that you had also the slow aggregation mechanism between when you have this very long lambda DNA spacer, is just a kinetic effect that the carpet formation or the 2D crystallization on the surface is just a bit faster for the long spaces than the aggregation in bulk, whereas when we shorten the lambda DNA, then we just reverse that. The aggregation in bulk is faster than the crystallization on the surface. This brings me actually to the end of my talk, and so what I can say is that highly specific and reversible self-assembly is possible with short DNA, but it is difficult to remember what I told you in the beginning, because you have many bonds in the, between two colloids. When you have short strands, your melt transition becomes very sharp, and that's really hard to control. One way people have started looking into that problem in the group Miriam Leunissen and Paul Shakin in New York, they have come up with a different way of controlling the number of bonds on the surface by using palindromic sequences that can fold back on themselves, and you can control the number of these loops by how fast you cool the system. But you can, if you can control that, you can run a programmable self-assembly. But DNA is also, what we showed actually with this study, is that DNA is a very perfect monodispersed long polymer that can be used to drive these this crystallization in 2 dimensions. And we see the fractionation. You have to be aware of the size distribution in your colloidal system as well. And just to show you what happens when you get the wrong batch of colloids, or you don't make them yourself, and they're polydispersed. Here, the polydispersity of the colloids was just too large, and they form also aggregates, 2D aggregates. That is a 2D carpet, but it's completely disordered. Incidentally, last year we bought a new batch, and they sent us one, and they said it's really the last bit of that batch, and it was disastrous. My students spent 2 months to reproduce data, and we all only got that. So realize polydispersity of your colloids is very important when you want to drive aggregation. This can end up in disaster when you don't have a computer, but just the real thing. So with that, I want to thank you for listening, and I'm happy to take your questions.
Yeah, Erika, I missed something crucial in what you were saying, which is how these assembled carpets sort of peel off the substrate, or what leads to that separation.
Which separation? Between green and red?
No. So you said the crystalline layers that you make are not stuck on the substrate, yes, but they're in the solution.
Yes.
Right? What leads to them? I guess they do form on the substrate.
No,
no.
They form. You have to imagine. I think you have to imagine that when they happen to come close, one colloid, but they don't come in. You have a long polymeric space, so you have weak attraction. What happens is they can still move on the surface quite considerably, several microns, and that's one sore point in our experiments, which I asked my students many times to do, but it's really difficult because you have very low concentrations. We are at 0.004 volume percent. The problem, you have still motion, and you can also still, they can move, but they don't move away from the surface. So that allows them to find each other and eventually to overcome the steric stabilization. But they are not sitting on the surface due to depletion like what people have done. See, we did some control experiments. Here in this case, what you do is you take exactly the same system, the same sticky substrate, but then you take the same colloid, the same lambda DNA, but you do not attach them to the colloid. You get random aggregates. And if you increase the polymer concentration, so the DNA concentration, you just get huge random aggregates. What other people have observed before was crystallization into on the surface. When a colloid comes close to a surface, you have a depletion hole of polymers there, and polymers press then, in addition, the colloid onto that surface. And there you do see occasionally also crystallization well below your liquid crystal transition.
In order to attach the DNAs. Because
Again?
How important the surface roughness of colloids are to attach the DNAs. And because polystyrens are known to have tethers on their surface.
Yes. I mean, the surface here is glass surface, and remember the colloids here, this is not to scale. Colloids are maybe this size compared to the sticky surface. So the colloids are one micron, and I think the surface detail of the colloid in this case does not play any role, because all the sizes involved, the radius of gyration of the DNA is so much is comparable to the colloid that it will not see any detail on the surface, I think. Is this what I...
This colloid surface are already attached with some tethers on it, right?
No. It's just a homogeneous glass surface. We just, from solution, absorb the polylysin pack. Polylysin is positive, glass is very negative. So you don't have any pattern on the surface. It's just homogeneous coverage of your polylysin pack, and in some cases also the complementary DNA. Yeah. So no preparation.
So you mentioned that lambda DNA is a naturally monodisperse long polymer, but how important is the monodispersity, how important is the role of this monodispersity actually in making these crystals? Because you said that even with a 200 nanometer length you could still form small crystals.
Yes.
So I wouldn't expect like a small difference in the monodispersity of the strand length to really affect the phenomenon.
It should affect it, because somehow our understanding is that they have to be kept, once they are close to a surface, they have to be kept in the same plane, say, in order to meet and to aggregate. If you have this polydispersity of your polymer, they could also sit in different planes and not interact as effectively. And I think that plays a role. And you could have easily polymers that are twice as long in a regular distribution. And okay, if something is floating up there and another colloid here, they are not going to crystallize. I think that's important.
Okay, and so the second question I had was, since these are 2D crystals, have you looked at the melting of 2D crystals? Yes. And is the mechanism similar to KTHNY, or is it like different? Or
what is interesting is we had battled on that question with a referee, and you see all these beautiful facets in the system when you have small colloids, colloidal carpets, and facets are indications of equilibrium structures, if you wish, because you don't have, if it's just sticking where it sticks, then you just get a fractal surface. So what we think is we have close to equilibrium crystals forming, but they fall into something like a secondary van der Waals minimum, enhanced now by depletion interaction due to the big polymer around. Because once they are about 200 nanometers apart, the colloids, and we heated up for several hours to 80 degrees, and they are not falling apart. They are really staying, although they should be melting, we do not see melting.
So I was wondering how flat are these flying carpets? Are they
Very flat.
very flat?
So there are your fluctuations in that we observe are of the order larger than, say, 10 or 20 times your colloidal radius. So the monolayer itself is more or less of the order of the colloidal system. It's not much more. Yeah. Shahul?
I wanted to ask, you showed a slide with the interactions decomposed. How do you actually measure these? And
I don't measure them. That's
okay.
This is estimated
Uh-huh.
just based on some standard textbook van der Waals interactions for two spheres.
And
This is, we measured the zeta potential of the bare beads and computed what then the Coulomb for our ionic strength should be. And this here has been done, people have done huge amount of measurements on measuring all interaction potentials, free energies between base pairs, but not just C and G, AT and CG, but also what happen, how they change in the presence of each other. So different, they are all sequence dependent, and depending on the concentration of the salt, added salt. It's important to have monovalent salt. If you take two-valent salt, you get clumping.
And what exactly do you mean by the DNA steric repulsion?
So,
because, you know, from this it looks as though it's being driven by van der Waals interactions largely, right?
But it's just only, van der Waals is only huge when they are very close. This is at one nanometer separation. Mm-hmm. So that falls off very quickly. So it's very weak van der Waals. I mean, the steric repulsion of the DNA forms is in a mushroom configuration around the colloid, and it's just a polymer. It's like a mushroom configuration of negatively charged polyelectrolyte, and they will repel, but how they repel, I don't know. Because if you take them just without the sticky overhang, they will never aggregate. We tested that. So it's just really steric repulsion.
Suppose if we use some anisotropic colloids like rods and plate-like structures, can we do we see these structures, these carpet-like structures? Or?
I think you will be able to see something like that. I know that Yevgenia Kumacheva in Toronto, what she does is they take gold nanorods and they form so-called pompoon structures where they attach longer polymers on the ends that interact with each other, and they form a very nice phase diagram of necklaces where they form one after the other, and if you go to higher concentrations, they form even sort of spheres, well-ordered spheres of the membranes of these rod-like particles. Yes. So I hope if we can make them perhaps with tobacco mosaic viruses or something like that, that's what we would like to do also, yeah.
Okay, thank you.
It's been slightly touched on earlier on in the questions. Can you measure bending rigidity and so on? Do you have fluctuations in these surfaces?
Yeah, that's the next point we are doing, but that's a bit delicate. What we try to do is now also to hold it with optical tweezers in one place and monitor the fluctuations of these membranes with just, but we are not, it's still difficult to make them, and it takes time. Let's put it this way. But I think it will be possible to look at this. Because, again, this one referee mentioned, it should not be stable when you lift it off the surface because fluctuations grow logarithmically with the size of your carpet or of your membrane. And the referee also said, I shouldn't say he because it could be a she, that we don't have hexagonal structure but hexatic structure. Obviously, I couldn't see that, but we try to measure these fluctuations, but it's not falling apart. Even when we lift it off, you have undulations, and we try to measure those. Yeah.
So one comment about this, Erika, here.
Yeah.
One comment about this is that, of course, it can grow as log L, but there might be a prefactor which is large.
Yeah.
My question was that there was a picture of your membrane, and then there were some colloid particles.
Yes.
Maybe you have already sort of answered this, but is there an exchange between these free particles and the crystalline membrane?
I was thinking about it, and I looked at it many times now, and very often I think you can have an exchange, and I think sometimes you see these beautiful defect structures where you have a single vacancy because one popped out. And when you look then very carefully, there is a colloid floating on top of that mismatches.
So this is actually in equilibrium with a gas and solid.
Initially, but once it's embedded in the membrane, I think it will be not possible to put it back in, simply because once you have that, you still have the thick DNA cloud that you don't see because it's not fluorescently labeled, but it's still a polymer layer that it has to overcome to stick back into.
You mentioned that you use sucrose to lift up these layers once they form.
Yes.
Am I right? So, I mean, once a layer is formed and if you lift, it is stable in the bulk?
Yes.
Okay. Okay, so it is not attached because close to the polymer it's because you have attraction. But even if you lift it in the bulk, it is stable.
Yes.
So you have like a long range attraction between the polymer and the crystal particles.
Not quite.
No, the surface is functionalized to begin with.
So the surface is a very thin functionalized layer of a few nanometers. This is really in principle a quasi-hard surface. Your colloids, once the colloidal layer forms, it is about a few radii of gyration of your DNA above. You can lift it up to 60, 70 micrometer above the surface. So there's certainly no interaction with the lower surface. So it's totally free floating. And you basically have a thin membrane of colloids with polymer on top and polymer on the bottom. Because the DNA is still attached. It cannot escape. But the lifting force is strong enough to overcome the stickiness to the ground.
It's a related question. Like when you have this this film, this colloidal carpet in the bulk, is it stable with respect to the introduction of defects? Like for instance, by optical tweezers, if you knock defects into your carpet.
Well, what we try now is we have a multiplexed optical tweezer where we can hold particles, up to 50 particles in a place, and see whether we can induce crystallization in a specific place where we hold this. But we haven't. But we tried also to pull a colloid out of the membrane. That's a bit tough because at the moment our optical tweezer, depending on we have a 60 times 63 times objective lens, water immersion, and it has a certain focal width. And that is of the size or a bit larger than the colloids. It's hard to pick out one, but even if you try to pull through it, they are very stable. You can't destroy them. And actually somebody in Ljubljana, I forgot his name, Cyril, I think, and Primo and others, they have done something similar where they take paramagnetic particles, and if you oscillate a magnetic field under a certain magic angle, you switch off the repulsion between the colloids, and they form also membranes. And there, what they did was to pull a large colloid through the membrane with optical tweezers, and it took a lot of force to get through. And once it's through, I think it immediately closed on to that.
Thank you.
Any other comments or questions? Well, thank you, Erika, for your fascination.
Thanks.